So in a previous video I built this, which is a little amplifier that goes with some speakers. It's just a very small, about 6 watts, I think, Class B amplifier. And if I plug this in and connect some speakers to it, oh, it also has a Bluetooth module in it. You can see that this has some issues. So if I power this on, it's going to do its Bluetooth thing, but it's very audible. I'll bring the speaker closer here. That it's humming quite a lot. It's quite audible. So if I unplug this again and we look at how this is actually made, there's some clues why it does that. So if I open this up, and it's just glued down, we look in here. This is a demo board for the what's the chip called? PA1517G by UTC, or Unisonic, I think they're called. So this is just a like a demo board I built a while back because I wanted to test the amplifier. But after I had built that, I thought, yeah, I already have the demo board. Why not build an amplifier based on it? And if you look at this, there's an issue that's pretty much immediately visible. This is where the power comes in to this power switch here, and then it goes off to the transformer, and it comes back out here, goes into the rectifier back there. And you can see right smack in the middle of all of that power section stuff is the actual Bluetooth module that I'm using. And this has a lead coming out here, this lead, that goes into the input of the amplifier. So this is right next to the power cable here and right in the middle of the power supply section. And that, among other things, is probably why it hums. One more thing is, if you look at the waveform that this produces on the scope out of the power supply, there's quite a lot of ripple on it. So that's another reason why this is going to hum. So the project for today is take the concept of this and make it better. And what I want to do here is I want to get this power supply module here, this Bluetooth module here, out of the power supply section, and I want to have some more control over the ripple on this. This regulator here, by the way, is for the Bluetooth module. This the amplifier runs directly off the unregulated power here, which is probably another reason why this hums. So let's put this aside and look at the schematic of what I came up with. Well, obviously another thing is this time we're going to make a real PCB, because I started making this because I already had this board. And that's why it's all on prototyping board. Okay, so here's the schematic of the board that I want to make. It starts out fairly similar to the other one, with the transformer coming in, and then it has a discrete bridge rectifier. On the other one, bring it up here again, we had an integrated bridge down here. These diodes are rated at 3 amps each, which is a little much, but better to overrate something than to have it overloaded. So they're about twice the rating you'd need, because the maximum current going through the amplifier is 2.5 amps, and these are 3 amp continuous rated diodes, but you have to keep in mind that they're only on for half of the cycle, and the other half of the cycle, it's the other pair of diodes, so you could run more current through these. could run 3 amps continuous through these, but what you're doing is you're running 2.5 amps for half a cycle through them. So it's a bit overrated, but it should be fine. Yeah, filter caps, 3 of them, smallish 100 nanofarad cap. I should say these don't have values on it. These are 1000 microfarads each, 16 volts, because the whole thing is running off of 12 volts. Small 100 nanofarad cap to further reduce the ripple because of the impedance and all. Then in the old version, we're going basically from here directly into the input of the amplifier chip. But on this one, we have what's called somewhat wrongly a capacitance multiplier here, which is going to reduce the ripple quite a lot. And we can look at this on an oscilloscope a little bit later. Basically, here's a 1K resistor and another 1000 microfarad cap, another 100 nanofarad cap, and a BD437. And that's going to reduce the ripple quite a lot. It's not going to provide any regulation or anything. The output voltage is going to change with the input voltage, and it's dependent on that we feed in the sort of right voltage. But this is fairly tolerant. It doesn't need a stabilized voltage or anything. It runs from, I think, about 8 volts to 14.4, and you can actually maximum run it at 18. But this is the absolute maximum rating. They say typical is 14.4. So that should work out quite nicely. And even if we have some drop here, if we feed in 12 volts, we get 12 times the power of the square root of 2. And even if we get some drop in voltage, once this starts working, we should still be fine, and this doesn't care too much about that. We've got a 7805 for the Bluetooth module just hanging off here. This is going to be less than 50% efficient. This is going to idle around 30% efficiency because it's actually burning away around 9 volts-ish. But since we're only going to draw a couple milliamps, this really doesn't matter too much. Yeah, and then this is the amplifier section. This is basically straight out of the data sheet. Important things here. This is capacitor coupled. Here's the output to the speakers. 2 1000 microfarad capacitors I put in here, which is what they recommend in the data sheet. These input capacitors are 220 nanofarads each. I use some, I think they're polyester film caps or Mylar or something, but they should do fine. This isn't an audiophile hi-fi sort of thing, it's just a little Bluetooth speaker. This pin here is interesting. This is the 1/2 VCC stabilizing pin, so you have to put additional capacitors on there. They recommend putting 100 microfarads on. I put 1000 and another 100 nanofarads. I went a little bit overboard with this time because I didn't want it to hum. So that's why there's probably a little bit more capacitance on there that you'd actually need. Okay, signal ground, power ground, and ground. Again, because I wanted to avoid hum at any sort of cost, I put in bridges here. So if I wanted, I could bridge all of these together. But if it should be necessary to separate them in some sort of way, I could just open this bridge and then run a little bodge wire somewhere where I wanted to have this ground connected. So, yeah. This is the standby pin. The standby pin is disabled by just permanently tying it to VCC because I don't need a standby functionality on this. Either it's going to be on and then everything's going to be on, or it's going to be off. I don't need standby because that's just going to waste a lot of power. And yeah, it's just going to waste a lot of power and do nothing if you put it in standby. It's not going to take so long to start up that it would actually be necessary in any sort of way. This is, I think this standby pin is more, if you want to use this with a microcontroller or anything, you could have this on all the time and then just enable this when you need it and save a little power that way. So while the whole thing is on. Yeah, VCC is just connected to here, and that's basically all that's on this schematic. So through the magic of video editing, here we are at the finished board. You can see it's fairly similar to the schematic actually. Bridge rectifier here uses different diodes than on the schematic, but these are 3-amp rated anyway. Capacitors, here's our capacitance multiplier, here's our 5-volt regulator. And here's the section where the Bluetooth module is going to sit. So this has just a solid ground plane under it, with the power connectors for the Bluetooth module here, and these are the 2 input pins for the audio signal, and this is the signal ground loop. Although all grounds are common at the moment, it doesn't seem to cause much of an issue. And then we've got the speaker output here. And if you have a closer look, think, oh, he messed up the footprint of the chip, didn't he? There's 2 pins too many here. And this is sort of correct, because I was working from the datasheet and I wasn't actually looking at the chips that I had. And I seem to remember I had the 20-pin version, but they also make an 18-pin version. And they also make a single inline version, which I'd really like to get my hands on, because single inline chips are just magical and great. But we're stuck with the DIP 18. And I thought I had the DIP 20, so I made a footprint for the DIP 20. The nice thing about this is that on the DIP 20 version, these 2 pins, they're just 2 additional ground pins. So on this chip, this whole side here is power ground and basically heatsink. So it just goes down to the copper plane and sinks away some heat. And they, on the 20-pin version, they just have additional 2 pins here for additional ground connection and heat sinking and that sort of thing. But if you have the 18-pin version, you can just plug it in like this, and the rest of the connectors are exactly the same, so you don't even need to change anything. One thing that I realized after I made this board is this is not really all that advantageous to have the chip off to the side like this. It would be much nicer to have it in the middle of the board, because if you look at this, instead of going to a nice big heat sinking copper plane, this is just going to basically a line of copper, and then the big copper plane is here doing nothing. So it would be much better to put it, well, to have all this circuitry up here where the chip is, and then have the chip down here in the middle. But yeah, that's how I laid it out. I already tested this for about half an hour. It's not getting too hot. I think we should be okay. But we'll see. At any rate, these chips, they don't cost a lot of money. So if I burn one out and learn a lesson that way, yeah, so be it. Yeah, I think it is time we look at some measurements here. So first thing we should look at is the power supply section. And for that, I'm just going to pull out this chip here. Well, it's probably going to be a bit easier because I have this additional piece of socket here. So chip is out. And now let's hook it up to the oscilloscope. So if the camera would focus. What I'll do here is I'll flip this around like this. And I already have some test points here. And I'm going to hook channel 1 here. I'm going to hook directly to the filtering capacitors, so you can see the ripple that that this produces. And channel 2, I'm going to hook up to here, which is after the capacitance multiplier. And then the last thing we need to do is we need some sort of load, because we're not going to see a lot of ripple while our power supply is idling. So I have, this is actually an audio test load, selectable between 4, 8 and 16 ohms. So each of these banks here is 8 ohms. So you can have, if you connect them in series, you can have 16 ohms. If you take one or this one, you can have 8. And if you parallel the two outer ones and the middle one, then you get 4 ohms. So this is kind of handy. But to test this, we're just going to use one 8 ohm block here, which is a little more than an amp. And that should give us an idea of how effective the capacitance multiplier for this is. So I'll just hook the leads directly onto here. Don't necessarily need the cables. And then I'm going to connect one to my ground point up here and one to this, like this, and hook the oscilloscope probe above that. One reason of doing that, the wire below that is going to have about an amp flowing through it, so the section under it is probably going to get hotter than the section that's only connected to the oscilloscope. So I don't melt more little slots into my probes, which I tend to do. Okay, so I'll set up the camera at the oscilloscope and then I'll connect it to power and we'll see what it does. Okay, I've got the camera set up at the oscilloscope here. We see our two channels. The bottom channel, the yellow trace, is the raw power supply voltage waveform. So directly taken off the filter caps after the bridge rectifier. And the other trace is the voltage after the capacitance multiplier. So this is what the load sees, is the upper trace up here. And what we should see if I turn this on is we should hopefully see a fair bit of ripple on the yellow trace and not a lot of ripple on the other one. So this looks like what we expect. There is quite a bit of ripple on here, and if you look at this, I've got this at 2 volts per division. So this is for almost 6 volts of peak to peak. And yeah, that's not exactly great. But if you look at the other trace here, you can see this is 50 millivolts per division now. So we have just about 60, 70 millivolts of ripple on here. And this is, I would suppose, quite acceptable for an amplifier like this to have 50 millivolts of ripple at almost full load on there. So I think that's just about okay. I don't mind that much. I mean, we could still improve this if we put more capacitance in there, do some more regulation, but for the sort of application that this is going to go into, I don't think it's necessary to have this smoothed down even lower. So, as I've said before, we can't do really any sophisticated testing because my audio signal generator is currently not working. But what we can do is can just hook this up to some speakers. It's the same speakers I hooked up to the other one before. And you can see if it hums any less. And even if I bring the speaker up here, you can see it is dead quiet. There's nothing out of this. Nothing. And see that it's working, because if I touch this, we're getting something. But what we can do, which is a little less sophisticated, we can use the bridge function generator, the old school bridge function generator that I built in another video, with the tube output stage. It's not ideal because it has a really high impedance output, but it should still give us a picture of what the waveform that comes out of this looks like in comparison to the waveform that goes in. So I'll set everything up, focus the camera on the oscilloscope again, and then we'll have a look. Okay, I've got the signal generator, the old school signal generator, hooked up to the amplifier, and this is the upper trace, channel 2, and channel 1 is hooked up directly to the dummy load. So the output from the amplifier is going into a dummy load, and it's hooked up directly to that. And if I put these two over each other, let's see, this is pretty good. This is pretty well reproduced actually. And it's at almost 20 kilohertz. It's doing that, so this is pretty good. I started with 20 kilohertz here because the 20 kilohertz bridge is the one that works the best in the signal generator. But if I go to the 5 kilohertz setting here, you can see this is still doing pretty well. And again, do the same thing here. These two over each other. This looks fairly good. And we'll also go down to, let's go all the way to 15 hertz. It doesn't look as good there, but also the signal from the signal generator looks a little crummy there. So maybe let's do 60 hertz. It's probably a little better. And if we compare this, it's still doing pretty well, I'd say. This should be more than enough to listen to some podcasts or something. So yeah, I'd say electronics-wise, amplifier-wise, power supply-wise, this works pretty well. The next step is to go to the other amplifier and rip out the Bluetooth module. In the last shot I actually messed up a little bit. I was hooked to the 8 ohm terminals on my dummy load when I should have used the 4 ohm terminals. But now I have it hooked up to the 4 ohm terminals, and if I lock the exposure down here a bit, you can see it's still doing pretty well, even though it's now feeding into the correct impedance. So yeah, the other frequencies are pretty much the same as the 20 kilohertz here, so it's also doing well at 4 ohms. Alright, I have this removed from the other amplifier that's in pieces somewhere over here, and it's shedding pieces as we speak. I have this connected here. This is the audio output going in here, and this is the power from the 5-volt regulator. And I'm happy to say this sounds perfectly fine. There's not a lot of hum on there. It is noticeably more than without the Bluetooth module. But I don't know if this is just a thing. If you plug in a headphone, if you plug in some headphones, if you'd also hear that in the headphones, maybe this is just a little bit noisy in itself. I don't know. Anyway, it's definitely acceptable, and I'd love to play you something over this, but I'm currently filming this from my phone, so I can't really connect via Bluetooth to this and play something while also simultaneously filming. But we'll solve this problem in the next video somehow. Next video is going to be about the speakers and the case. As usual, first video has the electrical design and everything. And in the next one, we'll design a case and probably use these speakers. I have a couple of these. And I think this would go quite nicely in a fairly slim case with the speakers pointing out the side like this. So we'll see. But this will all be subject of the next video. So bye for now, and I'll see you on the next one.